Weenies easy to make fun of. It's a lot of
We
fun.
do 10 together.
We can talk.
I'm very confused.
You got one. You got one?
Okay.
Who needed one? Okay.
So, I found there was an equation that you can use for 10, right?
There's any number of equations you can use for 10.
Like-
You gotta get more
Can you,
specific.
mine is,
We
yeah,
just let 'em-
I looked this up because I was very confused. It was like KE final, kinetic, so maybe it stands for kinetic?
Don't even.
No?
Don't.
Okay.
Don't.
I got the answer.
Bert, just please do
Just-
it.
Can we hear this answer?
Don't.
Just please do it.
I'm just curious about this.
KE final
1/2 mv squared.
plus UF equals KE initial plus UO.
Kinetic plus potential equals kinetic energy final plus potential energy final.
Yeah.
Bert.
Yeah.
Does that work?
It's just conservation.
Mr. Burkamp, couldn't you use A equals,
Anyway, what?
couldn't you use A equals G sine of theta?
Yes,
Yeah, that's what you're supposed to do.
you can. Okay, now, shh. Let's talk about number 2. Okay? So here's the deal, you've got an inclined plane, right? Now I was nice and made it frictionless, okay? So here's the bigger idea. When you let go of that block, what's the only force that's gonna make it accelerate? Gravity. And a component of gravity that we have determined that as a civilization that we're gonna call force parallel because it's parallel with the inclined plane. And you know, force parallel equals F of G sine theta, okay? Give you the weight, you know the angle, you can find your force parallel, okay? Now, but you ultimately have to have the acceleration of the block to figure out how fast it's going when it hits the bottom. So are there any other forces acting in the direction of this inclined plane? No. So that means that's also your net force, right? There's no applied force, there's no friction, there's no squirrels involved, no fans, no rocket engines, nothing. This is it. So that also equals your net force, right? Which is mass times acceleration. So this is what you ultimately have to end up with finding is that acceleration. So find your force parallel. Now the problem is you don't know the mass of the block, but can you find the mass of the block?
Yes.
Yes, because you know the weight of the block, divide that by 9.8 meters per second squared, voila, you're off and running, okay? So, because if 10A is wrong, everything else is going to be wrong, okay? So your acceleration on 10A should be like 4.9 meters per second squared, okay? That's, if you go through all of that, that's what you should get as your acceleration. No. Shh, shh. Because you got to have the acceleration before you can find the velocity. Okay? Because if your acceleration's wrong, then your velocity's going to be wrong. So when you get down to 10A, your velocity should be 3 point something. Okay? Slightly above 3 meters per second. Okay?
Is that second digit a 0 here?
Huh?
Is that second digit a 0?
No, the second digit is not a 0.
Okay.
It's 3.1 something. Okay? Because if that's wrong, literally, everything else is going to be wrong on the problem. Okay? So it should be like 3.13, something like that, give or take. Maybe that's exactly, I don't know. So, because you got to have the acceleration, then you're going to get your velocity. Now, on B, here's what's going to happen. You got another block down here. They're going to hit, and they're going to do the California thing, and they're going to move off together. Okay? So, as soon as you increase the mass, what has to happen to the velocity? Olivia? Why? Beautiful. I have to have the same momentum. Therefore, when these two move off together and do the California thing, right, you're going to drop your velocity. Now, at that point, there's going to encounter friction. Now, why did I make the frictional force negative when I typed up this problem? Yeah, you have positive velocity and your frictional force is going to be acting this way. Now, there's a couple of ways that you can do this problem to find the time. I don't care. One option is you go old school F equals ma. Okay? It's an option. You know the force. Now, here's the question. Which mass are you going to use? The first mass, the second mass, or the combined mass? Why? Yeah, they're moving off together. So this force is acting on both masses. So one option is that you can go old school F equals ma. Use the combined mass of the system, you know the force, you can find the acceleration. Then you can take that acceleration and run that into A equals V minus V naught over time. Okay? You find your acceleration. Now here's what you have to be careful of. This V naught here is the velocity that they have when they move off together. It's not the initial velocity of the single block when it hits the bottom. Okay? So this V naught has to be your answer from B, not your answer from A. Okay? Then you can solve for time, boom, you're off to the races. Okay, that's an option. If you're old school, F equals ma, okay, it's like, ooh, huge fan of Isaac Newton. Okay, fine, knock yourself out. It's cool. Now, the other option is you go, oh, but I like momentum, okay? I'm a momentum kind of person. Oh, I'm happy for you. So your other option is you can use momentum, and you can go force times time equals change in momentum, which is mass times, force time equals change in momentum equals mass times V minus V naught. So you can do it this way too. You know the force, you know the mass, you know your final velocity, you know your initial velocity, solve for time. Okay? You're going to do the exact same math. All you're going to do is alter the sequence. Okay? Either one of them is F equals ma. It's just written a little bit differently. I don't care how you get there. Just get there. And then on D, when you find the distance, there's a whole bunch of different ways you can find the distance. You can draw a velocity time graph and find the area underneath the velocity time graph. You can use that equation. You can use distance equals 1/2 V plus V naught times time. There's any number of ways you can find that answer. So here's the deal. On number 10, on letters B, C, and D, all of those answers on B, C, and D should be around an answer of 1. Okay? That's an ish, okay? But they all should be around 1. So if you have an answer of like 4 or 5 on B, C, or D, you have done something horribly wrong. Are we good?
No.
Anything else on the assignment? Logan?
11C.
Well, you can't talk about 11C without talking about A and B.
Gosh darn it. Mr. Burkamp, we did all the math right, but Mrs. Fair had us reset our calculator, so we were in radian mode. Says degree.
Because why would we ever steal answers from a math test that's fourth block, and why would it matter? Okay.
We got all of our math wrong because we were in radian mode because we had to
That makes
reset
me
it.
very upset. That's why I always gotta check your calculator, man.
I know, and like, it's funny because like ACT
Way
doesn't
to
even
go,
make
Matt.
you reset your calculator.
Thanks.
Thanks, Ms. Fair.
So like what did you have for the velocity on?
Our velocity on A was 4.40 meters per second.
What did you have as the acceleration?
Like the initial?
Yeah, no, just the acceleration when you use
It was
A equals C
negative
sine theta.
9.68 meters per second squared. Negative 9.68.
9.68. You have an angle of 30
Well,
degrees.
actually, that's not what I initially got because I did the math wrong with my calculator and made the note.
You had a 30-degree angle and an acceleration
Talk to him.
Yeah.
almost the same as free fall.
I don't know.
You trusted the oracle, didn't you?
Well, I trusted the math.
You trusted the oracle.
I trusted
No,
the math.
you trusted the oracle.
I did.
And didn't give it a second thought, did you?
No, because I thought I was in degree mode.
Huh?
Dude, like I said, man, you just gotta check it.
Okay.
Matt, shut your mouth.
They should make a physics calculator.
It's called a calculator.
That's just
Yeah,
called
they
a
do,
regular
it's called a
calculator.
Okay,
Should make a stupid gun.
so you have
Quick
Huey,
kills and weird.
Dewey, and Louie. Anybody know who Huey, Dewey, and Louie are?
That's from
Those
the movie.
stupid astronauts.
Show.
Is this Three Stooges?
No,
It's not the Three Stooges,
It's
that's
not the
Mo,
three-
Larry,
that's
and
Larry.
Curly.
Oh, yeah, it's
Curly.
Curly, yeah. I don't know.
They're the
He
nephews
just said
of
him.
Donald Duck.
Donald Duck, yeah.
Okay. Huey, Dewey.
Who needs that? What about Scrooge
So here's what's
McDuck?
important.
Scrooge McDuck.
They're just sitting there in space, okay? Right? They're sitting there in space.
Yeah.
Getting fairly bored, right? So what's the initial momentum of the system? A goose egg. Nobody's moving, right? So afterwards, what does all of the momentum have to add up to? Zero. Okay, that's going to be the main part of the story, okay? Because you cannot create or destroy momentum. Okay, that's the main point of the story. Now, if you're a numbers kind of person, what can you let the mass of each one of them be? 1 kilogram. Okay, you can use 10, you can use pi, I don't care, I use 1. Even if that, it really doesn't make any difference because it's all the same. So, I got 1 kilogram, I got 1 kilogram, I got 1 kilogram. Okay? So Huey pushes off Dewey. Okay? So, what's an easy velocity that they could have? 1. Okay. So Huey's going this way with a velocity of 1 meter per second. So what's Dewey going to do?
Go the other way.
With a velocity of? Not 1.
Negative.
Negative 1. It's a huge difference, right? Negative 1 meter per second. Guys, here's the deal. Every one of these problems starts the same way. Okay? Momentum of Huey plus the momentum of Dewey plus the momentum of Louie equals the new momentum of Huey plus the new momentum of Dewey plus the new momentum of Louie. They all start the same way. Now, this side over here is 0. So what that means is afterwards, everything has to add up to equal to 0. Now, Louie is not involved at this point, right? So whatever momentum Huey has, guess what? The momentum of Dewey is going to be equal and opposite. So if Huey is going that way at 1 meter per second, that means Dewey has to be going this way at negative 1. Or if you want that to be negative 1, he's going to have positive. It doesn't make any difference. So here's a common misconception. You think this side over here, the momentums have to be 0. I'm not saying the momentums are 0. I'm just saying they have to add up to 0. Okay? So at this point, Huey is going this way. Dewey is going towards Louie with a momentum of negative 1. Okay? So I got negative 1 plus positive 1. That adds up to equal to 0. We're cool. Okay? Now, Dewey and Louie are going to interact, right? Okay? They're going to interact. So if you look at how I laid this problem out, I tell you, right? Louie pushes Dewey back towards Huey with the same force as K. Then if Dewey comes to a stop after he's pushed by Louie, what will be the velocity of Louie relative to the velocity of Huey? So here's the deal. So you got this as a value of positive 1, this is a value of negative 1, everything adds up to equal 0. Now, we're actually going to have a new set of conditions, a new set of momentums. So, does the interaction here affect the momentum of Huey? When Dewey and Louie interact, is that going to affect Huey? No. Okay? He's cool. He's drifting off into space. See you, Huey. You're screwed. Okay. So, Louie is going to push on Dewey such that Dewey stops. Okay? Now, what does the momentum still have to add up to?
0.
0. So if that's positive 1, guess what? The momentum of Louie has to be negative 1. Okay? So that way everything still adds up to equal to 0. So basically, Huey's going this way, Dewey's stuck in the middle, Louie's going off in that direction to Burger King or wherever he's going. Okay? Now, here's another option. Dewey didn't have to stop. Okay, there's infinite number of things that could have happened here. But here's what, no matter what's going to happen, this interaction still has to add up to negative 1. So what you could happen is that you could have Louie going this way, like at positive 2 meters per second, and Dewey going that way at negative 1 meter per second. Okay? You could have that. And it wouldn't violate the law of conservation of momentum. Because then you'd have 2 plus, or negative 2, plus a positive 1, plus a positive 1, everything would still add up equal to 0. Okay? So no matter what happens, you still have to work within the confines of that momentum adding up to 0. Okay? Is everybody cool with that? Great?
So Dewey will be stuck, but he will also still have, before he becomes like stuck, he will have a positive velocity.
Yeah, if you define that direction as being negative, then Dewey's initially going to have a positive velocity that's opposite Huey's.
Yes. Yes.
But then when they have this collision, Louie's going to push on him and he's going to stop, and then he's going to take off going that way.
Yeah.
But no matter what, when you get done, all of the momentum still have to add up to equal to 0.
Okay.
We're good. Okay. Your answer far and away, the biggest one should be your answer to number 6, which should be 600 and some change. Anything else? Going once, going twice. So one of which has a little spring on it, which is cool. And if it really hurts if you put it up beside someone's head and push it,
Eli.
if you don't believe me, ask Nick Reiswig, he can verify that. Okay?
Ask Eli too.
Yeah, really. Seriously, like self-induced?
Yeah, no, he,
Well,
no,
first I did
he
it
did
to
it to
Maddie.
Maddie.
And then she said it hurt, and I was like, nuh-uh, I did it myself right at the temple, and it wasn't.
Legitimate pain.
Yeah, it was pretty painful.
How much force do those guys got?
You know why I don't teach freshmen?
To do stuff like
I heard
that.
you did at one point.
I did.
Oh.
I've done my time. I've done my
Do you
time.
not enjoy like exploring imagination?
This-
Isn't that what
this- now,
science
this
is?
is what I
Testing
told.
stuff?
This is what I told him. This was like 6 years ago. I took one for the team and taught like the freshman geoscience stuff. Here's the first thing I said. I said, "Here's what you're going to hear: is that I hate you because you're a freshman," and I do. So,
Teach
but I.
Connor Merrill.
Huh?
Connor Merrill. Do you remember him?
That doesn't sound familiar.
Aw, dang.
Okay.
That's Merrill.
But I told him, I said, if you act like freshmen, I will hate you. If you act like, high school students, we're going to get along great. And they understood that. And when they act stupid, someone would say, you're acting like a freshman, stop. Okay, so the other thing that's going to happen when you all do this, your table is actually going to be level and not like rolling downhill like this is, but pretend that this is level and this thing is moving. So here's what you want to do. You're going to put a 500-gram mass on one side, tape that down so it doesn't slide around, and then you're going to have the other cart. I don't care which one you put it on. You can put it on the one with the spring or the one without. I don't care. Pick one. Just put a 500-gram mass on there. So what you want to do is adjust the starting position so that after you release the plunger, they hit the edges at the same time. So here's the question. Do I want to start it right in the middle? Do I want to start closer to the weighted end or closer to the non-weighted end? Why?
Larger
Why is
mass.
it going to have a smaller
Larger
velocity?
mass, same momentum.
More mass, okay? So what you're going to do is you're just going to have to kind of start and kind of adjust this so that when you hit it, okay, and don't use your hand. This is why I've got Landon's calculator there. So you're going to go like this, okay? So they hit the edges at the same time. You're going to have two people timing, one person timing one person timing the other. Because what we're going to assume is that after it rolls, we're going to assume that the velocity is constant. And pretty much it is, yeah. And don't try and do this lab, with them flipped over. It's not going to end well, okay? I don't tell you specifically in the instructions, but make sure that you have the wheel sides down. So, here's the key assumption. Because of the fact that we're going to, and by the way, if your plunger won't stay in there, push that in and then take that silver tab and push that back in. That'll lock it in place. So, here's the key assumption. We're going to assume that this thing is going to, after it rolls and after that spring expands, that it's going to have a constant velocity. So, if you're rolling with constant velocity, what two things do you need to calculate that velocity? It's the simplest way to calculate velocity.
Or time,
Distance.
time and
Not distance, I want velocity. Question.
Thank you.
Huh?
D naught plus 18?
No. You're all making this difficult. I don't want distance, but it's close to distance. It rhymes with displacement.
It's placement.
Yeah, I want displacement, right? Now, what do you have to have? You look like, oh,
Well, distance is displacement.
no. No. Distance is a scalar quantity, displacement is a vector quantity. Because distance divided by time is speed, displacement divided by time is velocity. Okay. Now, what do you have to calculate displacement? You need two things.
Let me pull out the big dogs real quick.
So, you need two things to calculate displacement. Something minus something.
Here we go. I'm ready.
Final position.
Oh,
minus-
final-
Yes, final position and initial position, right? Dear Lord. Now,
It's like you learn the hard stuff, you forget the easy stuff. So it's like,
so here's the decision that you need
But
to
you didn't
make.
even learn the hard stuff.
And I don't care how you do this, but you need to decide as a group. If you want to go off where the middle of the carts are, that's cool. So in other words, like I'm going to put the middle of the carts at say 75 centimeters. That's cool. Then it's going to roll to the edge and it's going to stop here. If that's the case, then you need to measure where the front of the cart is here. So if you're going to go off where the front of the cart is here, then you need to go off the front of the cart here when it hits the edge. Same thing with here. This one's going to start here. This one's going to go when you stop it, figure out where that is. Okay? Now, the other option is that you go off the outside edges, and then it goes to 0, and then this one goes to like 122. Okay? I don't care which one you do, but you have to pick one. Because what you can't do is mark where the starting edge of the front of the cart is, and then measure where the back of the cart is over here, because otherwise you're going to be off by the length of the cart. So, I don't care. It doesn't make me any difference. Just pick a system. Either go off the fronts or go off the backs. Okay? So, you're going to hit it, it's going to expand, and then we're going to assume that these things are rolling at a constant velocity. Now, if you look on, so underneath like cart 1 and cart 2, I don't care which one you call cart 1, I don't care which one you call cart 2. Pick a system. Now, up there in the little boxes, that's where you're going to record your data. If there's an asterisk, that means that some calculation is going to be required. So, the first thing that you want is the weight of each cart. So how are you going to get the weight of the cart? Yeah, take a Newton scale, hang it up, boom, you're off to the races. Okay? Then how are you going to get the mass of the cart? Divide by 9.8. Yeah, so get one like this, get the other one like this, hang them up, boom, there you go, divide by 9.8. Then, and anywhere there's an asterisk, I have to see a calculation. And a lot of these calculations are going to be pretty simple. Okay, they're going to be usually it's something minus something, or like to get that velocity, you're going to have displacement divided by time. So, adjust your position, have one person timing one cart, have one person timing the other. Make sure that you stop the carts, don't let them roll off the edge of the table, and then they fall and they make a god-awful amount of noise and might become irritating. So let's not have that. So have somebody like stopping them, have some people timing. Got that basic idea? Yeah. Okay, there you go. Thanks, sir. Now, if I can stand up.
Oh, now I'm irritated.
Thank God awful.
There you go.
And now I'm irritated, and we didn't want that.
Okay. So, here's your setup. So, one cart's going to go this way, one cart's going to go this way. And to get this velocity, you're going to use displacement divided by time. So this is going to make this simple, because what we're ultimately trying to find is the momentum of the carts. So the momentum of the carts is going to be mass times velocity. So you're going to use this to get the velocity of the cart. Once you get that, multiply it by the mass, boom, there's your momentum. So what should your momentums afterwards add up to?
Zero.
Zero. So this is why you work off displacement versus time to get your velocity, okay? And not distance, because if it was distance and time, you'd have two speeds that would both be positive. This is why we work off displacement, because then they're going to be going in opposite directions. Now, when you get to that last column where it says force, okay? Listen to me very carefully because you all are horrible at reading instructions. To calculate the force, okay, you're going to go force. You're going to go force times time equals change in momentum. At this point, you will note the change in the momentum. What you're ultimately trying to find is how much force is exerted on the carts, okay? For the time in this calculation, use 0.02 seconds. And I tell you that in the instructions because you're going to use the 0.02 seconds because that's how long it takes for that plunger to expand, okay? You're going to use 0.02 seconds. Don't use the time that the carts are rolling, okay? Because the momentum isn't changing and that spring isn't expanding for 1 or 2 seconds or however long they roll. That spring is only expanding for 0.02 seconds, so that's what you're going to use in your force time calculation here for that change in your momentum. Okay? Cool with that? Okay. So wherever there's an asterisk, I want to see a calculation. Now, when you get to, on the back side, question number 8. So on question number 8, let me kind of give you a visual. If you want to set this up, you actually can. So here's your deal. And you're going to put a small block underneath the end that has the cart with the bigger mass. Okay? So in other words, we're going to run the exact same situation. But this one is going to go up, that one's going to go down. You're both going to start, it's going to start at 0, 0, just like this lab did when it was flat. Okay? So, this cart's going to go up, that cart's going to go down. Okay? So, keep that in mind because now you're going to have like an external force that's going to be acting on the system that you didn't have when it was flat. Now, before you actually start the lab, let me back up just a little bit. As a group, you need to do the pre-lab sketch of a velocity time graph. So what I want is a sketch of what the velocity time graph is going to look like for this situation where you have the two carts that are at rest, you hit the spring, and they go off of each other.
So do you need two different lines?
You're going to have one line for the more massive cart and one line for the less massive cart. Okay? But they're both going to be on the same graph. Okay? Let me give you a hint. The graph is going to start at 0, 0 because both carts are at 0. So before you actually do the lab, I only want one per group. Call me over. I'll sign off on it. Even though it is just a sketch and you're not going to know the numbers, but it has to be accurate in terms of are the times the same? Are the lines parallel? Or are they sloping? What's happening there? And make sure that you label which one is the more massive cart and which one is the less massive cart. So, back to the back side. Question 1 and 2 you can answer right here. 3 and 4, you do not have anywhere near enough room to answer those questions here. Answer 3 and 4 on another sheet of paper that you will attach to this lab. Put your answers on the left, put your work on the right, you all know the drill. Okay? All right. Any questions? So, if you want some shopping bags or if you want the cool stickers, then let me know. So, go, be free.